Greetings, I'm Kevin Hughes from the University of Bristol and the Heilbronn Institute for Mathematical Research. Today I'll discuss discrete restriction estimates for the curve xx cubed, which is joint work with Trevor Woolley. So for the outline of my talk, I'll give a brief motivation based on periodic PDEs. Then I'll go into the problem in the background before getting into the theorem and its proof. So discrete restriction estimates are useful in many settings, and in particular they're introduced by Bourgain in order to study well-posedness problems of periodic dispersive PDEs. In particular, he studied these for the nonlinear Schrodinger equation and the Korteweg-de Vries equation. More recently, Bourgain and Demeter have solved the L2 decoupling conjecture for the paraboloid, which made further progress on these topics. Solutions to translation and variance systems of additive equations is the second application of discrete restriction estimates, and these are Roth-type theorems. Okay. So for the Korteweg-de Vries equation, we start with our equation looking like this in 1, and we have some initial data f of x. We want to extend it to a solution u that satisfies our differential equation. In particular, we want our solution to be one periodic in the space dimension x and at each point in time t. Then Bourgain showed in 93 that the periodic KdV equation is globally well posed for initial data f lying in a Sobolev space whenever that Sobolev space has regularity s that is a non-negative integer. Okay. Underlying the KdV equation is the curve xx cubed, right? So if you take the Fourier transform of the KdV equation, you find this curve embedded in the exponential sum. And the way we can make that come to the fore is by considering the measure mu, which is just take all the integer points on the curve xx cubed, but truncate it inside some window of minus n to n. Okay, that's in the first variable. And since my little n is going to be between minus big N and big N, that means n cubed, of course, will be between minus n cubed and n cubed. So it's an anisotropic box. The Fourier transform of this discrete surface measure is then the following exponential sum. Right? I have one variable that is being weighted by n cubed, and the other variable will be weighted by n. This truncated extension operator for the KdV equation is then just the map that takes an L2 sequence to the weighted exponential sum, where I've weighted each of those phases by the sequence. And this is dual to the restriction operator, which takes a periodic function on the two-dimensional torus and then converts it via the Fourier transform into a function on the two-dimensional integers, so z2, and restricts that to the curve x cubed. Okay, but again, inside this window, minus n to n. So our main interest is actually going to be giving operator bounds on en, where those operator bounds are taking L2 to LP. And this is going to be, we want this controlled as n goes to infinity. So our precise problem is to make that quantitative. Right? I want to know, as a function of n, how I can control the L2 to LP norm for the extension operator. So Bourgain introduced this problem almost 30 years ago now. And in doing so, he implicitly gave a conjecture. That conjecture said that if I'm going to map from L2 to LP, then I satisfy the following estimates. Up to some constants, depending on only the parameter p, I look like 1, basically just a constant in some regime, or in another regime, I look like a power of n. Okay. Actually, what Bourgain worked with here was he gave up a little n to the epsilon, gave himself a little safety room here. And Hughes conjectured this explicitly, where they actually have a constant in the subcritical regime, that is when 1 dominates the term, the power of n. But they again conceded an epsilon, a power of epsilon in the factor of n for the supercritical regime. Whereas Trevor and I expect that there should be no epsilon loss whatsoever for any constant for any exponent between 1 and infinity. Okay. So where do these numbers come from? Well, let's start with the supercritical factor, that is n to the 1/2 minus 4 over p. If I just look at the L infinity norm, then the natural thing to do is to apply Cauchy-Schwarz, because that pulls out the L2 norm of your sequence. And when you do that, you're left with taking absolute values of a bunch of different phases. Okay, but how many phases are there? There's only n phases that you take, and since you've applied Cauchy-Schwarz, that gives you a factor of n to the 1/2, which you look at the power n to the 1/2 minus 4 over p, and when p is infinity, this just becomes n to the 1/2. Great. On the other hand, what about p less than infinity? Well, for that, we'll take our sequence to be 1 identically. Okay, the extension operator then truncates us to this window of a minus n to n in the variable little n, right? This gives us the following exponential sum. And if you take your frequency variables to be sufficiently small, very close to 0, that is, in something called the principal major arc, then you find out that this sum, this exponential sum, has essentially no cancellation in it, right? If you just take alpha 1 and alpha 2 to be equal to 0, then I get that my exponential sum has size precisely 2n plus 1, since there are 2n plus 1 ones to be added up. And that I'm claiming is hold true if I take a little neighborhood about 0, 0, right? The precise neighborhood is below. And when you compare that against the LP norm, you find this factor of n to the 1/2 minus 4 over p appearing whenever p is greater than 8. Okay, but what about the other term, the constant that we expect to dominate in the subcritical regime? Well, for p equals 2, that is mapping L2 to L2, we just have Plancherel's theorem. Brilliant. That gives us a constant of actually 1. Now, if you have a different moment, and which is an even moment, so instead of 2, we have 4, 6, or 8, or 10, or so on, then we find out that the exponential sum, that even moment of your exponential sum, counts the number of solutions to a particular system of equations. So for instance, when we consider the 6th moment, and that is we take the integral over t2 of our exponential sum to the 6th power, we count the solutions to equations where we have a cubic equation and a linear equation, each of which has 3 variables on each side of the equation. Okay, they're both homogeneous equations. Now, if you look at this system of equations, you can do one simple thing, and you can just take x1, x2, and x3 to be anything in your window of minus n to n. And then you can take y1, y2, y3 to be any permutation of them, and that gives you a solution to these equations. Now, for the 6th moment, it turns out these are basically all the solutions. They're not all of them, but that's the highest order term in counting the number of solutions. Okay. And these solutions we call the diagonal solutions. In other words, I'm saying any off-diagonal solution where the variables y are not a permutation of the variables x are of a much smaller magnitude than the diagonal solutions. Okay, this happens at the exponent 2, just from Plancherel's theorem. It happens at the exponent 4 and 6, and is conjectured to happen at the exponent 8. But we don't know if that's true yet. So a weak form of our conjecture, which is the implicit form in Bourgain's work, is one where we concede for any power epsilon, a little bit bigger than 0, we lose this power of n to the epsilon, and our factor, our constant, now depends on the exponents p and epsilon. Okay. Bourgain, in his initial study of the KdV equation, proved this conjecture when p was equal to 6. Huan-Li studied discrete restriction problems, and in particular attached to the KdV equation, and proved the same bound when p was equal to 14. Lai and Ding went further using recent work of Bourgain, Demeter, and Guth to prove this bounds when p is equal to 12. So I should say that whenever you have a bound, when you have 2 exponents, p1 and p2, and you want to look at an to LP1 bound and an L2 to LP2 bound, you immediately get an estimate for any P between P1 and P2. Okay. However, there is a regime change here. So when P is less than or equal to 8, the term 1 dominates in this factor. And when P is greater than 8, the power of n dominates. So if I have the right bound for any P greater than 8, for any P1 greater than P8, I actually get to interpolate with the right bound at P equals infinity and get the correct bound in between. Similarly, if I have the right bound for any P less than or equal to 8, then I get to interpolate down to L2 with using the Plantrel bound, right? And so the critical exponent here is actually P equals 8. And what this regime is missing at the moment is anything between P equals 6 and P equals 12, not including those endpoints. So the theorem for today is actually that we can get this for P equals 10. So Trevor Woolley and I showed that the weak conjecture holds when P equals 10. We don't show the sharp conjecture holds. So in particular, what we now have is that the range from P equals 6 to 10 is still open. Ignore that 8 here. That was a typo. Furthermore, based on some previous work with Kevin Henriot, extending Bourgain's epsilon removal technique, we automatically have that the sharp form of the conjecture is true for any P greater than 10. Great, so now that we've stated the main theorem, let's discuss a little bit about what we precisely prove, how we get to our main theorem, and then give the proof of what we precisely prove. So what Trevor and I show is that we have the following restricted type estimate from L2 to L10. So that is, I take an arbitrary subset between minus n and n, and say call that subset fancy A, and it has cardinality big A. When I apply the extension operator to this subset, the characteristic function of this subset, and look at its 10th moment, it's bounded by the first power of n times some exponential factor times the cardinality of A to the 5th. Now that exponential factor is known to be smaller than any positive power of n to the epsilon. Now, this is not the same as the strong type estimate, but up to losing or conceding another logarithm of n, we can apply the classical layer cake decomposition to immediately deduce the theorem I claimed a minute ago. So for example, you can see this is an exercise in Tao and Vu's book. This extension from restricted type to strong type. So let's give an overview of a proof now. We want to estimate the 10th moment of this exponential sum. Or in other words, the 10th moment, the L10 norm of our extension operator. Great. So what does this do? This actually counts, when you write this out and you use orthogonality, this counts the number of solutions to a cubic equation and a linear equation. But this time, our variables are constrained to lie in some set, fancy A, which is just a subset of the interval minus n to n. So how are we going to count the solutions to these equations? Well, we use the linear equation, to foliate the solutions in this system of equations. And each layer of that foliation gives us a similar set of equations, but in fewer variables. Then we use the special structure of these new equations to bound the number of overall solutions. So as a warm-up, let's see how this is going to work a little bit in practice. I again start with my window of minus n to n and my subset A to lie in that window. I take the characteristic function of A and I look at the 2s moment, or the L2s norm, where s is a positive integer. this counts solutions to a cubic and linear equation where there are s variables on each side. Okay, and each of those variables is constrained to lie in the set fancy A. Now, as before, if you just take your y variables and let them range arbitrarily over A for each of the variables, then you count at most the cardinality of A to the s possible solutions. What that leaves us with is we then want to bound the number of solutions in terms of the x variables equaling some arbitrary values that were given by just plugging in the arbitrary y's that we had. Okay, and we want to show that the number of possible solutions in the x's is very small. It's of order at most n to the epsilon for arbitrarily small epsilon. Okay, now it turns out this is actually easy to do when s is equal to 2, right? You just have x1 plus x2 and x1 cubed plus x2 cubed, and you see x1 plus x2 divides x1 cubed plus x2 cubed. And it's also easy to do when s is equal to 3, though slightly more difficult than when s equals 2. Okay, and Bourgain actually did that in a study of the KdV equation, which followed by adapting a method of Hua. All right, now let's actually start our proof. Again, our subset is going to be fancy A. It lies in our window minus n to n. And we're looking at the L10 norm of the characteristic function of that set, or the extension operator applied to the characteristic function of that set. So we have these two systems of equations. Instead of having all the x's on one side and all the y's on one side, I've jiggled them around a little bit in order to put them in a more useful form. So we take three pairs of differences on the left side and two pairs of differences on the right side in both the cubic and linear equation. Okay, where all my x's and my y's are constrained to lie in my set A, which I don't have any control over. It's just an arbitrary subset in this window. But they're not just one space points, they're integral points. Okay, so how do we do this? Well, we foliate by using the linear equation. And what I mean by that is I look at the left-hand side is equal to the right-hand side. And now that's going to be equal to some number, which I'm going to call h. Right? So in particular, I have this equation below. As h varies over z, I vary over all the possible choices for the bottom equation. Okay? And then I have to subject those to the additional constraint of the top equation. Great. So since my original set was light in this window minus n to n, then that forces h to lie in a slightly bigger window of minus 4n to 4n. That's great. That gives us a precise range of h that we'll use in a moment. How are we going to use that? Well, we have to write this for you analytically. So write out our L10 norm of the extension operator, and summing over all the possible values of h that we have for the linear equation, we arrive at this expression. And we're going to do what is normally a very bad thing, and we're just going to apply the triangle inequality, destroy all the oscillation in those sums, in those integrals. What that does is we lose a factor of n, which is our penalty. But what we've gained is we have a very simple 10th moment on the right-hand side, a very simple integral of exponential sums. Okay, maybe it's not very simple. We still have to analyze it, right? But the point is we've thrown away any potential oscillation above. And what we've gained now is that we can take h equal to 0. Okay, so now we're going to do a similar thing, but we're going to do it for the cubic side. Okay, so from before, we get that h is always equal to 0. And we foliate now in terms of the cubic equation for some other parameter L. Let CT of L denote the number of solutions to these equations. Where again, we are now suppressing the dependence on A in CT of L. But it very much depends on A because all our variables are restricted to lie in our set A. Via orthogonality, that is computing these exponential sums on the bottom here, we find that the LP norm, the L10 norm of our extension operator satisfies the following bound, right? We lose our factor of n, but it's at most this sum, which has two different components. It's a sum of factors C2 of L and C3 of L. See where CT of L was counting these differences being equal to L. All subject to a linear equation being 0. Okay, and our argument actually divides into two parts now. We're going to take L equal to 0 and L to be non-zero. So let's start with when L is 0. We want to bound C2 of 0 and C3 of 0. In order to satisfy our theorem, we see that we're going to need that to be at most n to the epsilon for all positive epsilon. In fact, it's that exponential, that bound in terms of e to the log over log log. So, all right, C2 of 0. That counts solutions to these two equations. I have a sum of two cubes equals the sum of another two cubes, while the sum of those numbers are equal to each other. Great. As I alluded to before, you essentially want to divide through by x1 plus x2 and y1 plus y2. Okay, there's a slight twist there. What happens if they're both equal to 0? Well, if they're both equal to 0, then we know exactly what x1 and x is in terms of x2 and what y1 is in terms of y2. And since they determine the other uniquely, we only have a possibilities for x1 and a possibilities for y1, and hence a squared possibilities for all four variables. Great. So what happens if their sum is not 0? Then we actually get to divide through. And dividing the cubic by that, you arrive at the following equation, from which you get to conclude by, say, taking the linear equation above and squaring it, adding it to this equation, you get to arrive at the product of your variables are equal to each other. And in particular, that means that the sets are the same. This again gives us at most 2 times the cardinality of a squared solutions. Okay, that's a squared from there and a squared from the contribution when x1 plus x2 is equal to 0, as is y1 plus y2. So altogether, we get at most 3 a squared possibilities for C2 of 0. Brilliant. The bound for C3 of 0 is very similar argument, but a little bit more nuanced or a little more subtle because of having a few more variables. Great. So for that, Bourgain showed that we have the following bound, where we have this e to the log over log log coming into play. And that's actually a divisor bound, a bound for the divisor function. Okay. So how do we do that? Well, we actually use a very nice identity. So if you look at it, so fix one set of variables. Let's focus on one set of variables, x1, x2, and x3. If I look at their sum and I cube it, and then subtract off the sum of their cubes, it turns out to have a very rich product structure encapsulated in the blue equation in the middle. What that implies is that when you use the cubic equation and the linear equation, you end up getting that you have an equation in terms of just products. And this is where the divisor bound comes into play. So in particular, if I have any two of the x variables summing to 0, then I know, like before, I'm going to have two y variables that sum to 0. And that collapses things so that I know, again, quite well what the variables are, how they're related to each other. And in this way, you can find that there are only a cubed possibilities. So if I instead assume that they're non-zero, right? I'm going to again want to divide through to show that I can apply a divisor bound. Now to do that requires a little bit of algebraic manipulation, but nothing too particularly deep. Basically, I'll look at those pairs in terms of their sum and show that they're related to each other. Okay, and you could do that. You do that again by making use of the linear equation. All right, and doing it in the proper way, you can show that you just apply the divisor bound in a straightforward manner and get the bound that we desired. Okay. So the way to do this is on the slides, and you can just pause to see the manipulations there. But moving forward to considering what happens when these C2 of L and C2 and C3 of L factors are not zero, or when L is not zero, we're going to arrive at the same bound, but the way the factors come into play will be a little bit different. Great. So let's just recall what those are. C2 of L is where I have x1 cubed plus x2 cubed minus y1 cubed minus y2 cubed is equal to L. And then I have that y2 is just a linear expression of x1, x2, and y1. Great. So I substitute y2, my linear expression for y2, into the previous equation. And what you get is you get a sum of variables cubed minus a sum of cubes. And you apply that identity again from before to get a relation between them and L. So now we actually have that these pairs of variables are entangled in terms of some divisor bound. And luckily, knowing any two of these divisors, we can recover any individual variable. Okay, so doing so, you get to apply the divisor bound again, which works because all the variables are at most n cubed, of order n cubed, which gives you this factor of e to the log over log log. Right. C3 of L isn't too different. And when you, so the way we're going to take into account now is we found the maximum bound for C2 of L for any possible L. So we just apply the union bound, and we need to find a contribution for all the C3 of L's. All right. So the way we do that is we write out what this sum means. It counts the number of solutions to this equation. Okay, because I say now that L can be anything between anything up to order n cubed, right? Each variable is constrained to lie in an interval of minus n to n, so their cubes are all, when summed together, at most 6n cubed. Right, but this just being a linear equation, well, I can easily bound that. I know that it's at most a to the 5th. So then I plugged in my L infinity bound for C2 of L, my L1 bound for C3 of L, and I get the bound that we claimed. Great. So just a brief look back at what we did. Our estimates for C2 of L and C3 of L encode the proofs for p equals 4 and p equals 6 estimates in our conjecture. These are already known or proven by Bourgain in the 90s. And this method, the even moment method, appears in much earlier work due to Cook and Zygmunt. The novelty of our method is that this subcritical estimate, which I mean the exponents p when p is less than 8 are subcritical, because the critical exponent is 8 if we know everything there. Then we interpolate with L2 and L infinity to get everything. So we take the subcritical information and we get to apply it in this supercritical regime. That is all the p bigger than our critical exponent. That is p bigger than 8. And it works quite well for us at p equals 10. This improves upon the p equals 12 exponent from before. So that's all I have to say today. Thank you very much for listening.